In 1989, deep learning was defined by the universal approximation theorem. It states a single hidden layer neural network can approximate any continuous function. The model recalculates its internal weights to thread the needle, mapping any input to any continuous output without error. However, while these networks possess the mathematical capacity to perfectly map any function, they often fail when transitioning from a controlled dataset to the noise of the real world. This occurs because the raw computational power required to fit any curve also enables a network to memorize its training data. This creates a system that is mathematically precise during training, but structurally fragile during deployment. Modern generative architectures employ structural workarounds to these foundational flaws, moving beyond the limitations of single-shot function approximation. The theoretical capability to learn any mapping is tied to the risk of memorizing noise over signal. Addressing this required changing how we structure deep learning tasks. Researchers took a standard image dataset and completely randomized the labels. A cat labeled a truck, a dog a plane. Despite having no semantic meaning, the network achieved near 100% accuracy on this training set, while test accuracy flatlined. The model did not recognize visual features or semantic concepts. It operated as a function approximator, finding a maximum likelihood estimate, memorizing the random noise to reduce its error to zero. This creates a rigid internal representation. When the network encounters out-of-distribution, or OOD data, inputs falling outside the precise coordinates of its memorized training set, the mapping breaks down. We see this in simple tasks, like training a network to colorize photos. Models will color the closed mouths of dogs pink because they over-indexed on training images where dogs had their tongues out. In high-stakes environments, OOD data leads to fatal errors. An autonomous vehicle recently swerved into a concrete barrier because that specific barrier was not present in the original training data. The model encountered a novel object and failed to resolve it. In these OOD scenarios, standard deep neural networks lack the architecture to calculate or express their own uncertainty. Standard deep learning maps inputs to outputs without a mechanism for self-correction. A model that memorizes its training data remains blind to the gaps in its own knowledge. Mathematical rigidity exposes adversarial vulnerability. Normally, we lock input data and shift internal weights to minimize loss. Adversarial attacks invert this, freezing weights and unlocking the input. A microscopic perturbation maximizes the network's error. By perturbing the input along the gradient, we force the network to assign an incorrect classification while maintaining maximum statistical confidence in that error. These vulnerabilities extend to the physical world. Researchers used a 3D printed turtle with a mathematically engineered surface pattern to trick computer vision models into classifying it as a rifle. Adversarial fragility is a mathematical consequence of relying on single-shot function mapping to process complex data. To bypass the memorization trap, modern generative architectures move away from single-shot generation. This shift is evident when comparing older frameworks like VAEs and GANs against diffusion models. Older models attempted to map from a compressed latent space directly to a final image in one pass. This was often unstable, frequently resulting in mode collapse, where the network produced only average, repetitive outputs. Diffusion models replace that mechanism with a sequence of careful iterative steps, beginning with what we call a forward process. We take a source image and incrementally add layers of random Gaussian noise until the image is pure static. This forward process is a simple mathematical decay that requires no training. The neural network handles the reverse process. Given a noisy image at step t, it predicts the residual noise difference from t-1. We optimize this using a mean squared error loss function, comparing the predicted noise against the actual noise added. Once trained, we feed pure random noise into this reverse loop. The network iteratively subtracts noise step by step, allowing it to produce diverse, high-fidelity generations. By asking the network to perform a repeatable, narrow task over multiple steps, diffusion avoids the fragility associated with single-shot function approximation. This iterative framework also applies to natural language processing. A large language model first performs tokenization. Raw text breaks into discrete blocks, encoded into numerical sequence IDs. The objective is autoregressive next token prediction. Given a sequence of tokens, it outputs a probability distribution for the next token. Because the training data consists of vast amounts of existing text, the data provides its own labels. This allows for massive, self-supervised training without manual annotation. The network's weights are optimized by calculating the cross-entropy loss between its predicted probabilities and the actual token found in the training document. As these models scale in parameter count and training data, we see step changes in their ability to handle complex tasks. The same next token prediction loop begins to generate coherent code, structure complex logic, and perform cross-lingual translation. These capabilities suggest that while the underlying objective is simple, the sheer scale of the prediction loop allows the model to capture deep patterns within human language. We can now connect the OOD data boundaries, the denoising timelines of diffusion, and the autoregressive sequences of language models back to the universal approximation theorem. The current frontier circumvents the vulnerability of single-shot memorization by adopting stepwise iterative optimization across both vision and language tasks. Even with these improvements, deploying these models in real-world scenarios still carries risks. Several frontiers remain unsolved. The field is still working to mitigate hallucinations, calculate explicit model confidence, and enable long-term logic planning. You can experiment with these concepts and build these architectures yourself on the Learn by Doing with Stephen YouTube channel. For ongoing discussions on the theoretical boundaries of machine learning, subscribe to the Stephen Data Talk podcast on Spotify and YouTube Music. Machine learning is no longer limited by the basic math of approximation, but by our ability to refine the sequences that guide its outputs.